Students, now we are going to see the topic transfer function of field controlled DC motor. So in the previous video we have seen the transfer function of armature controlled DC motor. Now we are going to see the transfer function of field controlled DC motor. The speed of a DC motor is directly proportional to the armature voltage and inversely proportional to the flux in field winding. In field controlled DC motor, the armature voltage is kept constant and speed is varied by varying the flux of the motor. So, how you are controlling the speed? By making armature voltage constant and by varying the flux. Okay. So, the flux can be varied by varying the field current. So, the electrical system consists of armature circuit and field circuit, but for analysis purpose only field circuit is considered because the armature is excited by a constant voltage or the armature voltage is kept constant. So, this is the field circuit and IF is nothing but the field current, RF is a field resistance, LF is a field inductance and VF is a field voltage and T is nothing but the torque developed by the motor and KTF is a torque constant, J is a moment of inertia of the rotor and the load and B is a frictional coefficient of rotor and load. The equivalent circuit of the field. So, this is the equivalent circuit of field. So, this is a resistance of field and this is the inductance of field. So, while applying Kirchhoff voltage torque to the circuit and we are considering positive to negative as positive. So, we will be getting IF into RF plus LF into DIF by dt minus VF is equal to 0. While taking the VF to the right hand side, we will be getting RF into IF plus LF into DIF by dt is equal to VF. The torque of a DC motor is proportional to the proportional to the product of flux and armature current. So, what is torque of a DC motor proportional to? The torque of a DC motor is proportional to product of flux and armature current. Since armature current is constant in the system, the torque is proportional to flux alone, but flux is proportional to field current. So, torque is proportional to field current IF. So, torque T is equal to KTF into IF. So, while changing this proportionality symbol, you will be getting a constant. That constant is nothing but KTF. The mechanical system consists of a rotating part of the motor and the load connected to the shaft of the motor. Now, this is nothing but the mechanical system or mechanical model of the motor. Okay. Now we are going to write the differential equation governing the mechanical system of motor. So, T is the applied torque and theta is the angular displacement due to this applied torque. J is a moment of inertia and B is a frictional coefficient. So, the differential equation is J into d square theta by dt square plus B into d theta by dt is equal to T. We can take it as equation 3. So, the differential equation governing the field control DC motors are RF IF plus LF into DIF by dt is equal to VF. T is equal to KTF into IF. Then J into d square theta by dt square plus B into d theta by dt is equal to T. Okay, these three are the differential equation governing the field control DC motor. Now we are going to take the Laplace transform of this equation. While taking the Laplace transform of this equation, you will be getting Rf into If of s plus Lf into s into If of s is equal to Vf of s. We can take it as equation 4. Now, while applying Laplace transform to equation 2, we will be getting T of s is equal to Ktf into If of s. Now, we are going to apply Laplace transform to the equation 3. So, J into s square into theta of s plus b s into theta of s is equal to T of s. Equating 5 and 6, we will be getting Ktf into If of s is equal to J into s square into theta of s plus b s into theta of s. From this, we can take, we are going to calculate If of s, and from these two we are taking theta of s outside. So, we will be getting If of s is equal to s into Js plus b by Ktf into theta of s. Now, we are equate the equation 4. From the equation 4, we are taking this If of s outside. So, we will be getting Rf plus s into Lf into If of s is equal to Vf of s. Okay. Now, we are going to substitute the value of If of s from equation 7 here. So, when you are substituting 7 in this equation, you will be getting Rf into Rf plus s into Lf into s into Js plus b divided by Ktf into theta of s is equal to Vf of s. So, in this motor, what is the output? Output is nothing but theta of s. What is input? Input is nothing but the field voltage Vf. So, what is transfer function? Laplace transform of output by input. What is the Laplace transform of output? Theta of s. What is the Laplace transform of input? Vf of s. So, we have to find theta of s divided by Vf of s. So, we have calculated theta of s divided by Vf of s. So, we are going to write this transfer function in a different way. So, from this transfer function, from this first term, we are taking Rf outside. So, we will be getting s into 1 plus s Lf by Rf. From this, you are taking b outside. So, we will be getting 1 plus s into j by b. So, we can write it, we can take Lf by Rf as Tf and j by b as Tm. So, this instead of this Ktf into Rf into b, you can write it as Km. Okay. So, this Tf is nothing but the field time constant. It is nothing but Lf by Rf. Then mechanical time constant Tm is equal to J by B. So, now we are going to see AC servo motors.